Welcome to Soil Structure Engineering Problems YouTube channel. This will be the lesson 10, and this is about the theory of plasticity. So we have reached a stage where we need to introduce more complex models, and the theory of plasticity gives us the framework to implement these models in commercial software or in software that we've developed by ourselves. So this theory of plasticity is certainly more complex than the previous theories we have been discussing in this channel, basically the isotropic linear elasticity, for example. So I will take the opportunity in this presentation to review concepts of elasticity and basically to cover all what is necessary to understand the theory of plasticity, which is a very important theory when you deal with soil structure interaction problems, because the soil will behave, let's say, following this sort of theories. So in the first place, in this lesson, we are going to introduce many things. So the first one will be to introduce the ingredients of an elastoplastic model, because plasticity is not usually isolated, but works together with elasticity. So we are going to review the most relevant concepts around isotropic linear elasticity, of course, that are relevant to understand the plastic theory. We are going to understand as well the failure theories and their relation with the elastoplastic models, because we have studied the failure criterions or the free criteria or the failure theories before, but they are related certainly with the elastoplasticity or plasticity theories. So we are going to see this relation. We are going to define elastic, plastic, and total deformation and its relation. And we are going to finally define the most important ingredients of this plasticity theory, which are the yield surface, the plastic potential, the flow rule, and the hardening, softening law that will have control in the, let's say, increment or decrement of the area where you are in elastic regime. So why we need to study plastic models in the first place will be the question for any students and for us in general. So certainly when you study elasticity, and specifically when you start defining in more details elasticity and you talk about isotropic linear elasticity, you notice that there are certain limitations, or it's better to say that there is a lot of limitations. There are a lot of limitations in this theory, because, for example, in a real material, you need to characterize the ultimate and failure states, and this is something that you don't usually do when you define the isotropic linear elasticity. You just define the behavior or the relation between the stresses and strains, which are linear, but you don't say precisely when or under what circumstances the failure occurred. So characterize the ultimate failure states is part of the plasticity theory. So this is something that you can do in a very simple way. For example, just defining the yield strengths in tensile stresses or compressive stresses in every direction. This is one way of doing it, but we need something more sophisticated if we want to be more realistic. So this is one of the reasons why we need plasticity, because we need to characterize then the ultimate of failure states in our theory that will reproduce the reality. In the second place, the model of linear elasticity doesn't capture the permanent deformation we usually see in materials, and particularly in soils. The most important deformation are permanent. The soil is not able to recover a lot of deformations under when you release the loads, so you are going to recover just a little, and the most important deformation will be all plastic. So we need a plastic theory to capture the plastic deformation, and the isotropic linear elastic theory does not allow us to capture these permanent deformations. So the third reason to study plastic models is to capture the change in behavior, because it's true that especially when you study metals, for example, steels, that is the metal that you study the most, when you are a civil engineer, you notice that there is a first regime, a first stage, where the relationship between stresses and strain is certainly linear and elastic and isotropic in many cases, but after that there is a change of behavior, changing the behavior to a more plastic or viscoplastic or any other non-linear behavior that is not isotropic linear elastic anymore. So we need to be able with the theory to capture this change, and the isotropic linear elastic model is not able to do it. So we need to introduce a plastic model or a plastic theory to capture this change in behavior. So in order to do that, of course, all the things that we usually do when we work with models will be more complicated than the isotropic linear elastic case, but it's something that we sometimes need to do for reasons of defining or having a model that is able to reproduce what's happening in reality. For example, on the screen now you see something that we saw before, but it's just to recap and to go in more details. So you see this space where in the vertical axis you have stresses and in the horizontal axis you have strains, basically. Define it as in the way we define it usually, these two concepts, stresses and strains. So I'm not going to explain more details about that. So in the first instance, you tend to divide, or you need to divide the behavior in two big groups: the materials that are brittle and the materials that are ductile. So for example, if you have a brittle material, let's say you have sand or you have glass, and you pull or you compress this material in the lab. For example, in this image you see a representation of the tensile stress in 1 dimension. So the behavior you will capture when you measure the stresses and strains is a curve that will start as a straight line, so a linear elastic behavior, and after a little bit of non-linear behavior, and the failure will be produced after that. But if you have a ductile material like clays, for example, or any other ductile material you can imagine, for example, the steel, after a while, as in this example in here, because this corresponds to a test made in a sample of steel, you will see that after a while, after this linear elastic behavior you have at the beginning, there is a change of the behavior and there is a plastification, we say, when we describe this sort of behavior. And when we start unloading and reloading, we see these loops in here. So what we notice is that it's not only that there is a change in the behavior and we start having plastic deformation, because in here you see that when you unload, you recover only part of the formation and you keep certain plastic deformation that will be there forever, even without loads. It's not only that, but it's as well that the strength that started at this value sigma y is going to increase to sigma y prime and to sigma y double prime if you continue loading and unloading and reloading. So this means that there is a lot of changes, not only in the structure of the material that produce this behavior, but changes that you need to capture with your theory or your model. And this is what the plastic theory allowed us to do. So in this example, in just 1 dimension, we see that the plastic behavior that presents this ductile steel is much more complex than the behavior for a brittle material. But so we need to introduce some sort of theory to capture all these changes and all these complexities that the reality show in a test. So in here there is a simple equation that just shows what is the recoverable and what is the permanent deformation in this case. For example, for the first cycle of loading, unloading and reloading. We are going to see in more details in a moment, but certainly when we talk about the difference between brittle materials and ductile materials, evidently the behavior is totally different. So it's something that we need to take into consideration when we set a model, when we implement a model, or we formulate a model, or when we propose a model to be used for doing these simulations. So Something that is a detail that we need to know is that the elastic strength is a value that is constant and is a property of a material. For example, for the steel will be around 200 megapascals. For the soil will be much less than that because the soil is not that strong. And the other parameters that are similar but they are called plastic strength will change with the level of loads and cycles of loading and reloading. So they are variable and they will depend on the level of strains. For example, you see here in this graph that for this strain, you have a new value for the strength, plastic strength, but if you increase the load and you go for more strain, you will have a bigger plastic strength at the end. So this will depend on the level of the strength in this example. So you need to capture this with your theory. One thing that is important is to understand from the beginning the concept of failure. When you are working in one dimension, everything is simpler. So, but even in one dimension, you see certain complexity already. But the failure that we mention and we read many times in books and articles is defined for brittle materials at the end of this curve you see on the screen. So when you reach this point, you will notice in the lab that the steel bar breaks, and that's it. There is no any more behavior to capture. And you notice that the first stage for the brittle material was linear and elastic, and probably what you are going to notice in the lab that this curve in here will correspond to a non-linear elastic behavior, because if you unload this steel before breaking the bar, you are going to probably recover almost all the deformation you had after the process of loading. In a ductile material, as you see on the screen, this is not what happened. What happened is once you reach the initial elastic strength, you will produce plastic deformation that you are not going to recover anymore. But the failure in a ductile material is far from the deformation of the strain corresponding to a brittle material. So a ductile material will allow you to deform more, and the final failure when you see the bar is broken is at this point at the end of this curve. But we define the failure in civil engineering and in structures when you reach the initial elastic strength of the material, because we don't want to see permanent deformation in our structures. This is something that is not good for us, and for practical reasons, we define that the failure is at this point and not at the end of this curve for the ductile material. And there is another reason why we define the failure when the yield plastification starts, is because in there we need to define something mathematically to be able to capture this change in the behavior from elasticity to plasticity. In the brittle material, it's not necessary because these strengths are very, very small. So, and because you are going to recover almost all of them, you don't need to define anything before the failure, because at the stage of the failure, in terms of load and strength, you will still have an elastic behavior. Maybe non-linear elastic, because evidently this is a curve, it's not on a straight line, but you will be able to recover all the deformation. So this is the reason why there is a distinction between the failure for brittle material and the failure for ductile materials. So the plastic theory will allow us to capture all the behavior after that point, the yield point we have defined for the ductile material. If we analyze in more details what happens in the behavior of this bar of steel in particular, that can be extended to other materials, we see that the first stage is the elastic regime. So this is something that we know very well, because we have been studying this isotropic linear elastic behavior before. So it's a very simple model because the relation between the stresses, which are the forces divided by the areas, and the strain, which are the increments in deformation over the initial deformation, the initial size of the bar, as is defined in here, is just an equation that has to describe this linear relationship. So, as you see, the Hooke law is the law that we use to describe this linear elastic behavior. So it's very simple to write mathematically, because sigma is the stress, force is divided by an area, is equal to the Young modulus multiplied by the strain, which is delta L over L0, which is the original length of the bar. And there is no complications to calculate this kind of stresses and deformation, because you have just a constant, the Young modulus, multiplying the value of the strains. Or if you are calculating the strain, you have another constant, which will be the multiplied by the stresses, and you will get the strength very, very easily. So there is no complication with this theory. And this expression, of course, for one dimension that can be extrapolated to the three-dimensional problems in matricial form. For example, this matrix form in here shows the relationship between all the components of the stresses, the axial stresses and the shear stresses, multiplied by this matrix, which is the stiffness matrix in this case, and multiplied by the this vector that represents the strain tensor, as we have mentioned before. So with all the components, the axial strains and the shear strains in here, or distortion, are called as well. So in a three-dimensional case, we can generalize the concept of the Hooke law and writing this equation, which is a tensorial or tensor equation, where sigma is the stress tensor, E will be the stiffness tensor multiplied by the strain tensor, will give you this relationship between these stresses and strains. So another thing that I will just comment, because this particular expression is for isotropic linear elastic materials, so it's an ideal material that is isotropic, which means that the properties, the elastic properties and mechanical properties, are the same in every direction, and they still follow this sort of behavior in general. And for this kind of models, it's very simple to define this relationship, because we need just two parameters, two elastic parameters, the Young modulus and the Poisson ratio, as you see in the expression. The other thing you can do, for example, because sometimes you need to calculate stresses in function of strains, but many times you need to calculate as well strains in function of the stresses. So you can do that by inverting the stiffness matrix and having this this other matrix in here, and it's going to be equally simple to calculate a strain and stresses, because you just have to know the value of the Young modulus and the Poisson ratio. As you notice on the screen, the compliant matrix or compliance tensor is called this C in here in compact notation, represent this matrix in here you can see on the screen basically. So this is because we have inverted E, and we and the inverse of E we call C usually. There are variations there depending on the book you are reading, but just to mention that this is the case in this case. So if we go a little bit farther from the point where we reach the yield strength, the elastic yield strength of the material, we are going to start noticing this plastification. So we abandon the linear elastic isotropic behavior that allowed us to load and unload and recovering all the deformations, and we are having now deformations that are not linear anymore, and actually they are not elastic anymore, because at some stage we unload the structure and the material. What we are going to have is this behavior, as we saw before. So we are going to follow this path, where we're going to reach some point when the load is equal to 0, and we are going to notice that there are permanent deformations epsilon b in this case, and the corresponding maximum elastoplastic deformation will be epsilon a. And considering these definitions, we are going to have this equation where we see in more details what is recoverable and what is permanent. And if we will reload from this point, we are going to follow a path that is parallel to the initial path in the linear elastic regime. And if we unload again in this area, when we have a new elastic regime, we are going to follow just this path in here, and until we are going to reach some point that is going to be, in this case, bigger than the previous one, the elastic one. So the new plastic strength will be bigger than the original elastic strength. But at this point, there will be a change in behavior one more time. So we are going to abandon the new elastic regime to go to the new plastic regime after this point A. So if we continue loading the bar, we are going to reach, for example, another point C, and you can do this at any stage. And if you unload and reload, you will have the same sort of behavior as before, creating a new elastic regime that is bigger than the previous one, because in this case we say that the material is presenting hardening. So this steel is becoming more and more stronger when you unload and you reload the bar, because you are increasing the value of the plastic strength that established the new limits or the new yield limit for the elastic regime. But the cost you are paying for this is that you have every time more and more plastic deformation. Because, for example, in the second loop of loading and reloading, you see that the plastic deformation is much bigger than the previous one. So in the first loop, you have only this plastic deformation at this, let's say in this example, which is not numeric, but is just theoretical. Let's say in this case, you have the same amount of elastic deformation than plastic deformation, but in the second cycle, you notice that the plastic deformation is much bigger, and the elastic deformation that is recoverable is more or less the same as before, and actually will be the same as before, approximately. So when you go to the plastic regime in your ductile material, you notice that the plastic deformation had more importance than the elastic one, because the values are bigger. And actually in a real material, in a real steel, you will notice that the elastic deformation is very, very small in comparison with the plastic deformation you can get after the elastic regime. So all of this is the description in more details about the reality, what's happening in the lab. But what we need to study is in which way we are going to describe mathematically this behavior, because we are looking here for a mathematical model to be implemented in a numerical code. So we have studied before this, but I will repeat the concept anyway because it's important. The most, let's say, simple elastoplastic model is this model that you see in here, more or less in details in one dimension, which is an elastic perfectly plastic model. So this model is a mathematical model. It's not a result from the lab anymore. So it's a mathematical model defined in one dimension, where we see a first elastic regime as usual, and the plastic regime is a perfectly plastic regime. So in this case, we don't have any increment of the yield strength when we apply loads and we unload and reload the structure, so we don't affect the yield strength of the material. The yield strength is constant and is equal in elasticity and plasticity. It's just a value that is fixed. So in this case, we lose the capacity to capture the hardening we have in here in this real test, but at least we capture the change in behavior, so we are capturing the change from the elastic behavior to the plastic behavior. So this model, even when it's simple, it's very simple, is able to capture the change from the elastic regime to the plastic regime. And it's able as well to manage unloading processes and reloading processes, capturing the plastic deformation because the introduction of this second line, horizontal line in here, that apparently is super simple, but is able to capture something important: the change in behavior from elasticity to plasticity, and the permanent deformation that we are not able to capture with the isotropic linear elastic model that we have been using before. So you see in here this equation that explains simply what is the total strain, which is the summation of the plastic and the elastic strains. And from there you can, of course, work out how to calculate the plastic strain just doing this subtraction from the total strain minus the elastic strain. Of course, in the reality, because the materials, like for example the steel we have been studying before, and different type of soils will present hardening or softening. So instead of having a material that's improved with cycles of unloading and reloading, you can have material that get worse in terms of the strength. So when you reach the plastic regime, you start losing strength in cycles of unloading and reloading. So a model more sophisticated than the perfect the perfect elastoplastic model is called as well, or as in here. There is another that is even simpler, or I don't know if it's simpler or not, but it's another alternative to consider that the first regime is just rigid instead of elastic. So until you reach the yield strength and you have perfect plasticity. This one is the previous one we studied in more detail, so this is the perfect elastoplastic model, but you have models that capture, that are bilinear, are called them, because you have two lines. The first line is for the elastic regime and the second line for the plastic regime. So in this case, it's a bilinear model with hardening, and in this case, it's a linear model with softening. So if you notice, these four models I'm presenting here in this screen. So in the first one, which is first rigid and after plastic, all the strains are permanent because you don't have any possibility. Once you reach the yield limit and you go farther, all the deformation are plastic, because because these lines are vertical. So the line of unloading and reloadings are vertical because we started vertical in the elastic regime, or the rigid regime, sorry. So if you unload the structure with this idealization of this behavior as this material behavior, so in this area, in this rigid regime, you don't have any deformation. You don't have any elastic deformation. You don't have any plastic deformation. But once you reach and you go farther the yield strength, you will have only plastic deformation. So this model, this ideal model, is a model of extremes, let's say, because you have material that initially is rigid and suddenly become plastic without no resistance, because the plastic regime is represented by this horizontal line. So this means that you have deformation without increments in the loads. The second model is a little bit better in the sense that it's more realistic. So you have a first elastic regime where you can recover deformation because the deformation will be only elastic. And after you reach the yield limit and you go farther, you will have plastic deformations, but parts of the deformation will be elastic. So you have the possibility to recover at least parts of the deformation, the total deformation you have in your structure. So in this case, there are elastic and plastic strains, and an important detail is that the yield limits in elasticity and plasticity is the same and is constant. The same thing happened in the previous model. When you have a hardening model, a bilinear hardening model, you have elastic and plastic strains after the yield limits, and this increase the yield limits after unloading and reloading. And this is the reason why we call this model with hardening. In the softening model, there are elastic and plastic deformation and after the yield limits. Of course, what you notice is that the yield limit decrease if you start making cycles of unloading and reloading. So in these models where you have elastoplasticity, you will use the same equation for the elastic regime. In this case, I have put the relationship between strains and stresses as differentials, because just in order to be able to capture any non-linearity, and because when we reach the plastic regime, we are going to be forced to work in increments, because we need to capture the change in behavior of the yield strength, and we need to capture any unloading or reloading process that is able that the structure will be subjected to, because our model is now more sophisticated and is able to capture not only the loading and unloading and the plastic deformation that this will produce, but as well the changes in the yield strength in plastic regime. So we have to change now the nomenclature in here and clarify that we are going to work in increments. We cannot work anymore in total strains and stresses as we did in the elastic model, because we need to capture every single change when we go further in terms of loads, because we are in the plastic regime already. So in an elastic, linear isotropic elastic model, you don't need to do that. You can work in total stresses and strains, because the relationship between these two tensors, the stresses and the strains, are linear through this other tensor in here in the middle that have only constant. But when you go to the plastic regime, your yield strength will depend on the level of strains, so you are not going to have a linear model anymore. Even when the elastoplastic model is bilinear, because evidently in here we have a bilinear model in all the cases, so you have an initial line and a second line. The second linear model is not linear as the elastic model, because in there you have a parameter that change with the level of strains. So this is why we need to start working with differentials in here instead of following the same strategy as before, that is simpler because you have a multiplication of a matrix by a vector only. So from the computational point of view, the linear elastic isotropic model is super simple. But in here we need to work with differentials, because even when we say this model is bilinear, the second linear model that corresponds to plasticity is not actually linear anymore, because the parameters that define the model depend on the level of strains, as we are going to see in more details in a moment. So all of this is relatively clear in one dimension, but we have to remember that these processes occur in 3 dimensions in a real structure or in a real solid structure interaction problem. So we need to extend the concepts we have studied in 1 dimension to the 3-dimensional world. And in order to do that, for example, one crucial things to define in a plastic theory is to define the failure. And this is when complicated things start happening. So in this unidimensional model, it's relatively simple to define the failure, because we are saying this is our limits. As we saw before, if you remember, when we started this definition, the failure is defined when the yield strength is reached in a ductile material. So when we do that in a one-dimensional model, it's very simple, because in this case and in this case it's just a value which is constant, so super simple. And in this one, in this bilinear model with hardening and softening, it's a little bit more complex, because we have a first elastic yield strength and after we have an increment in the value, but it's still simple because it's just a parameter that increase, let's say, following this this slope in here, this linear relationship, but it's change, and it's going to depend in at which point you decide to unload and reload. So this is the complication, but it's still simple in one dimension. In order to identify when we reach the yield strength in a three-dimensional problem is much more complicated, because we need to consider all the dimensions on the spaces of stresses. So what we do to establish in 3 dimensions what is the yield strength, or when we reach the yield strength that will change the behavior from elasticity to plasticity, is when we define what we know as the yield surface. And the yield surface is a surface that is defined in a particular space, is the space of the principal stresses. So it's not any stresses, so it's defined as usually in the space of the principal stresses, because the principal stresses are 3 in 3 dimensions. So it's something that we can represent in a graph. For example, in here I have a generic yield surface in this space of the principal stresses. So it will be a surface that will define something that is crucial in our models. So is the state of stresses in your material, the soil or the structure, is inside this area we are going to define as the limit, the yield limits in 3 dimensions. This means that you are in an elastic regime. When you reach the surface, you are going to be in a plastic regime. So you will start developing plastic deformations. And to be outside this area is literally impossible, because remember that we are talking about the mathematical definition of the plasticity in here. So we are going to say that mathematically it's impossible to be outside this surface. So we are generalizing the concept of the yield strength in 3 dimensions, but in a space that is the space of the principal stresses. It's not the 3-dimensional space where we live in. It's the 3-dimensional space of the principal stresses. And we are generalizing then the yield strength in every direction, considering these 3 principal stresses. We are going to be able to calculate the plastic strengths using this yield surface. So this yield surface is absolutely fundamental for us. And this surface will allow us to identify in our mathematical model when we change from elastic regime to plastic regime. And this surface is going to be able to capture hardening and softening as well. When we have hardening, this surface will be able to expand, and when we have softening, this surface will be able to contract. Because, as we said before, the condition we are going to use mathematically, the mathematical condition we are going to use is that the plastic regime can occur when our state of stresses is over the surface, but cannot go beyond. So if we are in plasticity, we are on the surface. If we are in elasticity, we are inside the surface, inside the region that the surface defines, but we never can be outside this surface, because this surface is the limit from the position in this space we can be. It's not mathematically possible to be outside. And this mathematical condition is this equation you see here. So the equation that defines this surface in the space of the principal stresses and subjected to certain parameters that will be the parameters for the hardening or softening. So for the expansion or contraction of this surface is equal to 0. So this is the mathematical condition to say we are going to be able to be inside the region defined by the yield surface. We are going to be able, we are going to be able to be inside the region defined by the yield surface, having elastic regime, elastic behavior. We are going to be able to be on the surface having plastic behavior, but we are not going to be able to be outside this region defined by the surface, because mathematically we are going to say this equation is equal to 0. And this equation again includes as a variables the stresses, the stress tensor, and the parameters of hardening or softening. The reason why we choose to use this space of the principal stresses is just because if we choose to use the more general space of all the stresses, the axial and shear stresses, we are not going to be able to sketch or to plot this surface. But of course, mathematically, you can define, and you will define, the surface using the complete stress tensor, but in order to make a graph and to see the shape of the, and to study the shape of the yield surface, we are going to do it in the space we can see. It is to say an space with 3 axes only, the principal stresses in this case. Okay then, so we have reached these concepts in the first part of this videos about plasticity theory. So we have defined the yield surface for 3-dimensional problems. So this make me to remember the definition of failure or failure criteria or failure theories. And indeed, if you are thinking about failure theories related with this yield surface, is precisely this what we are defining here. So this is a general explanation of what is a failure theory. So you define first a region. This region defines a volume where inside you have elastic deformation only. The surface defines the region where you have plastic behavior in terms of stresses and strains, and it's impossible to be outside because the only way to be outside is to make the surface expand or contract. So what we are going to say here is that the yield surface for from the theory of plasticity is let's say a failure theory that is a little bit more sophisticated, because the failure theory we have defined before, and the failure theory that are defined in many places in books and other videos, say just that if you are inside the volume defined by this surface, you are in elastic regime and you are safe. If you touch the surface, you are in failure, and if you are outside the surface, you are, or the region defined by the surface, you are in bad conditions. But the plasticity theory go beyond, and with this surface control the hardening and softening that we notice or we observe in the lab when we test materials. So, but definitely there is an association between the yield surface defined for the in the plastic theory and the failure theory we have studied before. And this is what we are going to say or to describe after this slide. So, is the relationship between the failure theories defined in a classical way and the plasticity model we are going to implement or we are going to use in a computational geomechanic approach for simulating our problems of soil structure interaction. So I just added in here that a detail that is an important detail. So this yield surface can expand or contract, so it's not fixed as we have studied before when we studied classical theory of failure. So the process of loading and unloading and unloading and reloading are the processes that control or affect the size and the expansion or contraction of these surfaces, the yield surface, depending on the material you are trying to simulate. So the next step in this video should be the failure theories and the connection with the plastic theory. But in order to be sure that you understand what I'm talking about, I wanted to refresh a little bit basic concept of continuum mechanics and starting with the definition of the stress tensor. So remember that the stress tensor is a matrix or is a tensor. There are many ways of defining this, more or less complex, but for us it's enough to say that it's a matrix like this, where you have the axial stresses in the diagonal in red, and you have the shear stresses in these green components you can see here, and the representation is this infinitesimal cube where the axial stresses act perpendicular to the faces and the shear stresses act on the faces of this cube. And there is a system of principal stresses that you know, because you studied this before. If you start rotating the initial cube with the axial stresses and shear stresses, sooner or later you will find the direction of the principal stresses, where the axial stresses are maximum and the shear stresses are equal to 0. This is the characteristics that present the stress tensor, the Cauchy stress tensor we use in our applications usually. And in this case, the matrix will be this matrix with these diagonals, sigma 1, sigma 2, and sigma 3, which are the principal stresses. And the zeros correspond to the shear stresses, because by definition, and this is a property of the stress tensor, where you have the principal stresses, you have 0 shear stresses. This can be studied, for example, using the Mohr circles in 2 dimensions or 3 dimensions, something that we probably will be studying in the future in more details, but I have mentioned before. And the other thing that you can say as well is that there is certainly an order between these principal stresses, that we usually say that the sigma 1 is the greater, is the biggest, but of course, depending on the state of the stresses, all of these can be equal, having a spherical stress tensor, for example, or sigma 2 could be equal to sigma 3, or sigma 1 could be equal to sigma 2 and sigma 3 be smaller, or something like this. So all the combinations are valid. But the important concept in here is that there is always, for every state of stresses at every point of your structure or soil or system, to be more general, 3 directions that are perpendicular one to each other, and they correspond to the direction of the principal stresses, which are the maximum stresses, axial stresses, and where the shear stresses are equal to 0. The other important concept regarding stresses and the stress tensor is that any stress tensor can be divided or can be splitted in 2 components, one called the spherical stress tensor and the other called the deviatoric stress tensor, following the nomenclature in here. So basically, the spherical stress tensor is the average of the axial stresses multiplied by this I in here, that is the delta of Kronecker, or you can call this as well the unity matrix. It's a matrix like this with just ones in the diagonal. So when you multiply this value sigma m by this matrix, these units in matrix, you get the spherical stress tensor. And the deviatoric tensor is the one that is in this represented in here. So it's the original stress tensor minus the spherical tensor, and this is the shape in matrix form. And this is important because the spherical components of the tensor produce only changes in volume of your soil or your structure, but not in the shape, so it doesn't produce any distortion. And the deviatoric component of this tensor, the original stress tensor, produce only changes in shape but not in volume, so produce only distortions. And this is very, very interesting and important because simplifies the study of our problems. For example, let me just show you in here the consequences of this having this characteristic of spherical tensors producing only change in volumes and deviatoric stresses producing only distortions. You see that there is a decoupling between the change in shape and change in volume. And this is what you see in here, more or less, is that when you have axial stresses, the axial stresses produce, because these values in here are different to 0, produce only axial deformations. But the shear stresses produce only distortions. because all these components in here and here are equal to 0. So this is as a consequence of this property of the stress tensor, they enable to be decoupled in spherical stresses and deviatoric stresses, because this happened not only for the stress tensor, but this happened as well for the strain tensor. And this is why we have this property that is very convenient for us to be able to decouple these two problems and not to have this coupling between these different components in nature, because one of them are axial and the other are shear, and the same thing for the strains. So this is a property, fortunately for us, that simplify a little bit the treatment when we are studying the relation between stresses and strains. So another thing that is important to know is that this deviatoric stress tensor that control the distortions have, and any tensor actually, have invariants. For example, here we can recognize this I1 is the invariant of the stress tensor. So if you have a stress tensor like this, for example, the summation of sigma x, sigma y, and sigma z is equal to a number that is equal to the summation of sigma 1, sigma 2, and sigma 3, because independently of the orientation you give to this cube, the summation of this diagonal is the first invariant of the stress tensor, and is actually the first invariant of the strain tensor as well. So the summation of the diagonal of any tensor at any point of your structure or soil is a constant. So this is something that is very useful for some applications. And the deviatoric tensor is a tensor, so the summation of this diagonal will be constant as well, and in this case it's going to be equal to 0 because it's the deviatoric stress tensor. But the funny thing is that this tensor have more invariants. So the first one is equal to 0 for the deviatoric stress tensor. The second have this funny expression in terms of the shear stresses, for example, and this in terms of the axial stresses and shear stresses. And you can as well write this invariant J2 in function of the principal stresses. And there are other invariants. For example, the determinant of this tensor is equal is a constant as well, independently of the orientation of the you are considering for this particular deviatoric stress tensor. And this will be useful for us to define some of the plastic theories we are going to study in a few moments. So just before going to the next slide, so for example here you can express the second invariant for the deviatoric stress tensor in function of the second invariant of the stress tensor, the original one, and the first invariant of the stress tensor. So this is a relation you can find mathematically just to add to this explanation. So these invariants are very useful when we define models, as we are going to see in a moment. So this is the strain tensor. So this is a relative for to the stress tensor, and as you know, the diagonal is just the axial strains, so that control the volume of the cube we are considering. I have sketched it in here in 2 dimensions for clarity, but of course this is the same cube in the 3-dimensional space as in the definition of the stress tensor. And the distortions in green in here just control or represent the distortions or the change in shape of this cube that we are using to define the stress tensor and the strain tensor. So again, I have added in here that the spherical component produces only changes in volume and not shape, and the deviatoric component produces only changes in shape but not in volume, because this is an important thing to know about this this model we use. These models we use. So I have mentioned about this already. So we can go to the definition of the classical failure models. So when we talk about failure in 3 dimensions, the problem is that it's not easy to see the failure as is simple to see in a unidimensional test. For example, when you are pulling a bar of steel in the lab and you are defining a unidimensional test of stresses and strains, it's very simple to associate the stresses, the strains, and the failure, because you can see it actually, and it's very simple to see the failure in a curve when you do the test. But the problem is to define the failure when you have multiple loads in multiple directions, because in that case it's not simple to find a value that will give you the definition of the information you need to say that the material is failing. The failure in 3 dimensions is very complex, and this is the reason why there is not actually any theory that fulfill the requirements for making simulations, realistic simulations in problems in civil engineering. So especially in soils, because the soils are materials that are complex in nature. So for example, if you start thinking about the first theory we have studied, that is the isotropic linear elastic theory, this is applicable to steel and in general to metals in the elastic regime that present in reality, because the metals are certainly isotropic, so they present the same mechanical properties in every direction. They behave in a linear elastic behavior, at least for a range of loads, but in soils it doesn't happen like this. Soils are materials that are usually anisotropic, so they have different properties, mechanical properties in different directions. They are made by particles, so they are not even homogeneous as the metals are. And the other thing is the failure is difficult to characterize, because the soils are, the fact that they are made by particles make the soils, for example, and the geomaterials in general, good taking compression forces, but very bad having tensile forces, and not so good taking shear stresses or shear forces. So it's very, very difficult to characterize or to define a theory that fulfill all the requirements for every problem we have. So this is the reason why there are several, many theories, but we are going to discuss here just the most relevant ones for this explanation, because remember that in here we are more interested in solid structure interactions, problems in civil engineering. So the 4 failure models or failure theories I'm going to present here are the von Mises model for ductile materials. So for example a clay. Tresca model as well is for a ductile material as a clay, because the clay is more ductile than sand. Of course, this is a very general distinction. We are going to study the Drucker-Prager model as well for brittle materials, and the Mohr-Coulomb model for brittle material, which is probably the most famous models in soil mechanics, the Mohr-Coulomb failure criteria, and there is a reason why we're going to mention in a moment, but it's for a brittle material as well. So this is the yield surface for the von Mises model failure theory that we are going to use in our plastic models. So basically, what you see on the screen is that the shape of the surface is this cylinder that is concentric with the hydrostatic axis in the space of the principal stresses. And you see that this circle have, of course, because this is a cylinder, have a radius. This circle have a radius which is initially constant. But adding the concept of hardening or softening we have studied before, this means that this surface will be able to expand and contract when we use it in the context of the plastic theory. So this is the equation I have mentioned before. So this is the equation that says that the plastic deformation are produced only when you are on the surface. If you are inside the region defined by this surface, you are having only elastic deformations, and you are not able to be outside the surface because this is equal to 0. So the only way you can deform plastically is being on the surface and expanding or contracting the surface, but you cannot be outside the region defined by the surface. So in this definition is based on the second invariant for the deviatoric stress. This is the reason why I have included the explanation of these invariants before. And this is the yield strength. So this is the definition of the surface that give us this cylinder in this space. So evidently for these models that are thought for ductile materials, the failure is not going to be produced by hydrostatic loads that produce hydrostatic stresses. So this makes sense because certainly the materials are not are very good taking these hydrostatic stresses, especially under compression and especially in the case of soils, for example, but not good taking distortions. So this is the reason why this failure criterion is defined in terms of the second invariant of the deviatoric stress, because we are looking here for distortion that will produce failure. So this yield surface in this von Mises model of failure is not depending on the spheric stress tensor. This P is the average stress, axial stress, and it's not depending on this angle that is called the Lode's angle. That is an angle that we are not going to explain in details, but it depending only on the second invariant of the deviatoric stress. We said before that the yield stress will allow us to calculate the plastic strains. So in here we see that if this is the view of this theory perpendicular to the axis of hydrostatic stresses, we are going to see a circle. So this circle will allow us to define directions of plastic deformation when this surface is expanding or contracting, for example. In this case, I'm showing it here when the surface is expanding. So we are going to need to know the direction depending on the point on the surface we are, and the value, the quantity of this plastic deformation when the hardening is being produced, as we saw in the experimental test in the steel, for example. And you see here a set of equations that show the actual calculation of this plastic deformation, just as an example. You don't it's not my intention for you to understand these equations in details, because you need to know you need to have skills in tensor algebra. But basically in here you have an increment, the plastic deformation, that is calculated through this increment of this parameter lambda, and the partial derivative of the surface that define the yield surface in function of this derivative is in function of the stress tensor, basically. So operating this, you can find the expression for this derivative, and finally you have the plastic deformation in terms of the deviatoric stress tensor plus multiplied by this differential of lambda, a parameter you have to define. So in matrix form you can see the calculation of the plastic strains, and there is an expression in here just for you to have an example of the total strain is going to be equal to the elastic strain plus the plastic strain that is calculated finally with this expression in here. You can recognize that this y will be the yield strength, or the initial yield strength of, or the most probably the plastic one. So this will be non-linear, because this will depend on the level of strength. And this h is the most probably the plastic modulus that define the plasticity. Is a parameter that define the type of plasticity you have. If you have, for example, a bilinear model, this h will be a constant because it's just the slope of the second line of your model. But this y in here, if this is the plastic strength, will be variable depending on the level of the strength. Yes. So this is the reason why I said that even when this is linear, and this look like it's linear because it's the second line of the bilinear model, it's not actually linear, because there is a dependency on the level of strength to define the values of these parameters at least. So you see now the relation. So this is the classical von Mises theory, failure theory, that is connected with the plastic theories, because we are using this failure theory as a yield surface in a plastic model to calculate the value and the direction of the plastic deformations. So the failure theory is much more than a failure theory now. It's part of the plastic theory. Another thing you have noticed when you work with models is that we are always able to post-process something that is called the equivalent von Mises stresses in 3 dimensions. So when we have a problem, and we did that in models we have studied in previous videos, you show in colors the levels of the equivalent von Mises stresses, for example, in the soil around a pile or a group of piles, or in the group of piles itself, or in any other structures. So this equivalent von Mises stress is precisely the stress that is defined in the von Mises model. And this is the reason why it's a very simple way of analyzing your results is when you see the levels of the equivalent von Mises stresses and you compare with the yield strength, the elastic yield strength, you know, because it's a property of your material, you have an idea of how good or how bad you are in terms of the stresses, state of the stresses in your structure of soils. Because this is the expression in function of the principal stresses of the von Mises model. So basically, this expression in here is equivalent to the expression in here, but expresses in terms of the principal stresses instead of the invariants. But this equation in here, you see that have included the yield, the elastic yield strength, or this could be the plastic if we are including hardening. But the thing is, in your model, you can show easily in the post-process the equivalent von Mises stress, and you can compare with the value you know, because you have to define this value in your linear elastic model or in your linear elastoplastic model. So it's a simple way of making a comparison to know more or less the level of the stresses you have in your problem to calibrate your model if necessary for representing or reproducing some particular real situation in a problem. So the next model is the Tresca model. So this is very similar to the von Mises model because in terms of shape is more or less it's very close, let's say, because it's an hexagon that defines this shape in the space, but the same comments apply, the comment we made for the von Mises stress. So this is not looking for failures when you have massive stresses that are spherical, because evidently you will be moving around this axis and you are not going to produce failure because of this, unless you put a cap in these models, because in this model and in the previous one, initially there is not any cap, so this can be extended to the infinite in both directions. But if you add caps, so you are adding a condition to study the possibility of failure under hydrostatic stress states. If not, you don't have any limits. So, but initially, the model is not looking for failure under hydrostatic, under load that produce hydrostatic state of stresses. It's looking for failure when you have distortions or when you have deviatoric stresses produced by the loads. And this is the reason why the equation again include the second invariant of the deviatoric stress and the yield strength as well. That will be the plastic when you reach the plastification. And in this case, this model, for example, include the angle of load that we are not going to study, but because this model is very similar to the von Mises, so it's preferable to use von Mises to Tresca, but it's good to mention that there are other models, And the other thing is, you can notice in here very easily, is when you have to define the direction of the plastic deformation in this model, you have certain problems in these corners of this hexagon, because in this corner you have two directions. So there is an inconsistency in this model. Sometimes it's resolved with making this corner a round corner instead of this sudden change in direction. but evidently the von Mises stress, because it's a circle, is much more effective in terms of the definition of the direction of the plastic deformation. Unfortunately, for real applications, sometimes we need to use Tresca, because Tresca will give us a better match with the experimental results. But mathematically, the von Mises model is simpler, and sometimes we prefer to get a simple model than a more accurate model, because this model will be more stable. Anyway, you have the expression in here for the calculation of the plastic stress strains in this Tresca model. Just for your interest, if you have any interest in knowing more, it's just an example. And we can go now to the other models. For example, let me just check if we are following the right order. Okay, we are going to leave the Drucker-Prager for the end. So the molecular model is, I mentioned before, is one of the most used and famous models in soil mechanics and geotechnical engineering, because this model is a model that includes two parameters that are very well known in the community in civil engineering, and it's the cohesion and the angle of internal friction. So basically, you have two parameters to relate on clays, because the clays have the cohesion as let's say as one of the main parameters to define the behavior, and you have the angle of internal friction for sand. So this means that even when this molecular model is more for brittle materials, and you have the possibility to study clays as well when they are present. So of course, the selection of the model will depend on many factors. Simplicity is one of them. So von Mises is always a model that is more consistent and simple to implement and simple to use, because it's very, let's say, strong in the sense that it's very well defined. This model is a little bit more complicated to use, and as you know, the soil will be difficult to characterize. We are going to have different layers, anisotropy, and sometimes we are going to have a mixture of soil that we cannot define precisely if you have a behavior of a clay or a sand, because the mixture, depending on many factors, will have one characteristic or another. So, but anyway, it's an attractive model when we know the cohesion, when we know the angle of internal friction. And as you see in the definition of this surface is not only dependent on the deviatoric stress, so it's not only depending on failure by distortion, it's as well is taking into consideration the failure of load that produce hydrostatic state of stresses, because there is a limit. There is a limit in here where you are approximating to this, and this area is usually the tensile area, so it's the smaller one. When you start having tensile stresses in soils, it's very convenient to have this definition in here, because you will fail with very low loads that produce tensile stresses, because the soils are unable to take any tensile stresses. This bigger area in here corresponds to the compression, so load that produce compression. So when you have a lot of compression, you amplify the region of failure, because, as you know, more compression you have in the soil, more compactation, and the deeper you go, you have better, bigger values of the effective stresses that improve the strength of the soil, because, as you know, the strength of the soil depends on many factors, but it's not only the nature, it's not a property only of the soil, but it's in this model, the strength of the soil depends as well on the level of effective stresses. So this is the reason why the shape of this model is different. So it's a kind of pyramid with this hexagon, irregular hexagon as a base. And again, this can be capped at some stage, depending on your needs to reproduce reality. But this is one of the reasons why this is, let's say, popular. I have added as well the Drucker-Prager model. The Drucker-Prager model is similar to the Morculum model, in the sense that the shape is more or less similar. So it's a kind of cone in the space of the principal stresses, and the surface, the yield surface, is defined in terms of the average stresses of the spherical strength tensor and the deviatory stress tensor using the second invariant. So you see that this model follow the same, let's say, principles, in the sense that there is certain limits in terms of load that produce axial stresses, hydrostatic axial stresses, and it take into consideration as well the failure, because the distortion is attractive because as you see in the Morculum, you have the same problem as in the Tresca model. So you have these corners that produce inconsistency in the direction of the expansion when you are calculating plastic deformations. And this one, because it's a circle that is not constant, but again, this is a soft surface that allows you to be very consistent when you calculate the direction of the plastic stresses, strengths. So you see that this model use as well as parameters that are in function of the angle of internal friction and the cohesion. So it's very convenient as well when you are working with mixtures of soils that include clay and sand. But as we said at the beginning, the model you use depends on many factors. Every problem is different, so you will need to choose what is the model that serves you better to reproduce the reality. Here is an example of an expression for this model in order to calculate the plastic strains. And finally, I put in here that this is interesting because you usually study the Morculum failure theory in 2 dimensions, where in the vertical axis you have shear stresses and in the horizontal axis you have axial stresses. So you can, let's say, you can see, or you can recover the concept of the Morculum failure criterion in 2 dimensions if you project this model in 3D on this space where you have the deviatoric, how it's called, this is the invariance of the deviatoric stress tensor and the average stresses, axial stresses in the horizontal axis. So doing that, you recover the concept of this straight line that represents the limit of the state of the stress in the Morculum model in 2 dimensions. So the yield surface then have these equations to define the modeling mathematically, let's say. So you have okay, so in this third part, we are going to recap a little bit. So we have studied the concept of the yield strain surface, and I have here on the screen now again the 4 bilinear models I had presented before. So we have the perfect rigid plastic model, the perfect elastic plastic model, the bilinear with hardening, and bilinear with softening model. We have generalized some of the concepts of these unidimensional models to the 3-dimensional space. So if we go and recap a little bit about the concept we have introduced, for example, the yield surface for a plastic theory is going to be a surface that is in function of only on the stress tensor and plotted in a space, in a 3-dimensional space of the principal stresses. And when you have, for example, a perfect plasticity, which means that you have a model like this or like this, so you have a perfect rigid initial stage of an elastic stage at the beginning, and after a perfectly plastic regime, in those cases there is no any parameter to be defined in the yield surface, because the yield surface will be fixed basically. So the yield surface is not going to expand, the the yield surface is not going to contract, because the only parameter you need to define is the yield elastic stress, that is just a value and is going to be fixed. When you have hardening or you have softening, in those cases, if you generalize the concept to the three-dimensional space, you will need to create, or you will need to define a surface, a yield surface, with extra parameters, and the number of parameters will depend on the complexity of your model, in order to control the hardening or the softening of your surface, or your yield surface, that will be expanding or contracting. This is why here we express this as a general vector epsilon I, but in all the cases, in the perfectly plastic model, the model with hardening or the model with softening, this surface need to be equal to 0, or the expression that represents the surface is equal to 0, because this is the condition of being only on the surface when you are in the plastic regime. So the expansion and contraction will be controlled by this set of parameters. Could be one, could be two, or could be many, depending on the complexity of the model you are implementing and formulating. So again, in here I stated that the stress must state inside. When there is inside of the region defined by the yield surface, you will have elastic regime. When you are on, you will have plastic regime, but you cannot be outside this area created, or this volume created by this surface. So in here, a way of representing that you are inside the region established by the yield surface is to say that the equation of the surface is less than 0. So you have only elastic deformations on those cases. And if you are on the surface, you have a combination of elastic and plastic deformations. So it's important that once you activate the plastic model and you are on the surface, it's important to notice that you will have elastic and plastic deformations at the same time. And this is the reason why you needed to define the relation between the total strain is equal to the elastic strain plus the plastic strains, and the plastic strain will be the difference between the total strains minus the elastic strains. So this is the condition that take control of the fact that the elastic and plastic deformation are produced when you are on the surface, in the sense that you are under a state of stress that is on the surface itself. When you have the simplest model, elastoplastic models, sometimes the parameter that control the expansion or contraction is only one. And in this case, for example, we can write something like this equation, this general equation, where you have the surface, the yield surface in function of the stress tensor plus a parameter, and of course equal to 0 for the same reason that we have explained before. So this is just a particular case where the yield surface is defined by the stress tensor plus only one parameter, because this theory in particular is simpler. To calculate the plastic deformation, you have two alternatives basically. So you can use directly the yield surface that define your failure or the transition from the elastic to plastic regime, or you can have an additional surface that is called the plastic potential, and the plastic potential will have a shape that could be similar or different to the one you have used for the yield surface. And this is because depending on the complexity of the reality in terms of the result you get, the information you get from the reality, maybe the yield surface is not going to be the proper one to calculate the direction and the values of your plastic deformation. This is because, especially in soils, when you have a very complex materials, you will need to work with these two surfaces in a separated way, so you will have the yield surface to establish the point where you make the transition from the elastic to plastic deformation, and another surface, the plastic potential, to derive the plastic deformations in terms of direction and in terms of value. So the flow rule is the equation that is the general equation where you see there is a differential in here that controls the value of the plastic deformation, and the direction is controlled by the derivative of this plastic potential function G that is derived by the stress tensor, because this is the variable that's define the shape of this surface in the space of the stresses, or in the space of the principal stresses, if you want to see it in the three-dimensional space. So of course there are many cases where the plastic potential and the yield surface are the same. So in those cases we talk about associates plastic model. And if you have different surfaces for the yield surface and for the plastic potential, is a non-associate model, so a more complex model. But in any case, the equation you use to derive the value and the direction of the plastic strength is the one that I'm showing you here. So for a generic or a general three-dimensional problem, we have defined the yield surface and the plastic potential to be able to calculate the values and directions of the plastic strength. So when you have hardening or softening, or even when you have this perfectly plastic regime, you have the possibility to unload and reload. So in some cases, let's for example study this elastoplasticity with hardening. At some stage you can unload and you will be again in the elastic regime until you reload and you reach again the new yield strength. So you need to have control in your model about this situation as well. And in order to do that, you need to define a few more things. So the plastic strengths are calculated then using the yield surface or the plastic potential. So we have said that when the yield surface and the plastic potential are the same, that could happen, the model is to be set associated. The plastic strength components, what this means is the plastic strength produced by axial stresses and the plastic strength produced by shear stresses are related one to each other. And they are related through the flow rule we have defined before, where we have a differential to calculate the value and a derivative from one of these two functions, f of g, in regards of the stress tensor, in order to establish the direction. But this direction and this value of the plastic deformation, we have two components, the axial component and the shear component, so they are related, they are not decoupled as in the case of the isotropic linear elasticity. So the plastic strain depends on the stress state, not on the applied stress increments. This means that we are going to establish a very small stress increment, and we are going to say that the dependency of the parameters, the plastic parameters we have in regards of the strains, will be depending on the plastic strengths only and not in the increment itself, because if not, we are going to have a problem that is going to be very difficult to solve, because remember that this problem is non-linear, and the more complex your model, the more unlinear or non-linear will be. So we need to have certain independency at some stage to have the possibility to apply what we know from linear models and to resolve the small time step or the small stress step we are applying in our calculations by differentials. So once we know the direction, for example by the flow rule, we need to calculate exactly the magnitudes of this deformation we have, And because when we are on top of the surface, we have a combination of the elastic and plastic deformation or strains, we need to check where we are exactly, because what can happen, as we saw on the screen before, when you unload, you maybe go inside of the volume defined by the yield surface and you are not having plasticity anymore, but you have a new elastic regime that you need to define mathematically. So the condition to be on the surface was defined before, so is that this equation that defines the surface is equal to 0, and the condition that allows you to recognize if you're still on the surface or not is what we know as the consistency condition, that say that the differential of this surface is equal to 0. So, because remember that because this surface can be expanded and contracted, is not trivial, it's not easy to guarantee that you are still on the surface or you went to the elastic regime. So this is the reason why you need this consistency condition to be checked step by step in the resolution of your problem. So in summary, what are the ingredients you need to establish and you need to understand when you are playing or when you are using a plastic model are the elastic deformation that are exactly the same as in the elastic linear problem as before. That could be isotropic or could be orthotropic or anisotropic for more complexity. You need to define a yield surface that includes the values of, or depends on the value of the stress tensor at every point of your problem, plus a parameter or a set of parameters that control the hardening or the softening. You need a plastic potential to define the direction and to be able, to define the direction of your plastic deformation. And you need a flow rule to establish the value of this plastic deformation that will allow you to calculate the total plastic deformation that will have components, of course, but they are dependent one to each other. You need a hardening law to establish in which way the plastic yield strength grows, or any other set of parameters your plastic theory needs in order to have control in this increment or decrement. If you have softening, you need to calculate the plastic deformations, and you do it using a tangent matrix or the tangent tensor, because you are working in differential, because remember that this regime is always nonlinear, and the total deformation will be just the summation of the elastic deformation plus the plastic deformation. So with these 7 ingredients, you will be able to formulate in the first place and after to implement this in a numerical code. If you are using a commercial software like ANSYS Workbench, for example, all of this has to be defined in one way or another in order to be able to use plastic models when we do simulations in soil structure interaction, or when we study structures alone, or when we study the soil alone in geotechnical problems. Thank you very much for watching.